In this video, we are going to look at the Unit 7, Lesson 8 practice problems. Number 1 says, suppose a circle is divided into congruent slices. Match the number of slices with the resulting central angle. So remember that a circle totals 360 degrees. So we're just going to take 360 and divide it by each of these number of slices, and that's going to be our central angle. So 360 divided by 2 gives us 180. 360 divided by 3 gives us 120. 360 divided by 4 gives us 90. 360 divided by 5 gives us 72. 360 divided by 6 gives us 60. And 360 divided by 8 gives us 45. For number 2, we're taking a circle of radius 12 units is divided into 8 congruent slices. What is the area of each slice? And what is the arc length for each slice? So let's just take a look at this so we have a visual here. So we're going to take and divide this into 8 congruent slices. And we want to find first the area of a slice. Okay, so how much is one of these slices covering? And then we want to do the length of one slice's arc. Okay, so that's kind of what we're looking at. So we would take the total area of the circle. So let's do area, which is pi times the radius squared. So that's going to be 144 pi for the entire circle. And then we're going to divide it by 8 since there's 8 equal slices. And so that will get us 18 pi units squared for the area of each slice. And if you wanted that in a decimal, you could type that into your calculator, 18 times pi, and get approximately 56.5 units squared for each slice. Arc length is part of the circumference, so part of the whole way around. So for circumference, we do 2 times pi times the radius to get the entire circumference, which in this case then would be 24 pi. So then we're going to divide that circumference into 8 equal chunks and get each little slice of the arc is going to be 3 pi units. Again, you can type that into your calculator to get approximately 9.4 units for each little arc there. Number 3, Diego says to find the arc length, divide the measure of the central angle by 360, then multiply by the area of the circle. Do you agree? Show or explain your reasoning. Arc length is part of the circumference, not the area. So we wouldn't want a portion of the total area. We would want a portion of the circumference. So no, I don't agree, because arc length is a portion of the total circumference, not part of the area. So multiplying by the circumference instead. So if we wanted to change what he was saying, we would want this to say circumference. All right, and number 4, it says, we've got this triangle shown, sketch the inscribed and circumscribed circles for this triangle. So you just have to sketch them. You don't have to actually construct them. Remember that an inscribed circle will touch each of the sides and be on the interior. So if I try and get one here, that's pretty close. For an inscribed circle. And then the circumscribed circle will be on the outside and go through all 3 points. So we want it to go through all 3 vertices at the same time. So let me just play around with this until I get one that's close. So something like that. And you can just, like I said, sketch those in your book. And then we just want to kind of compare and contrast these. circles. And so we see for the circumscribed circle, so let me just start typing this and let me put it in blue. Okay, so the circumscribed circle is fully outside of the circle or of the triangle. Okay, so we see that it's on the outer part of that triangle. It doesn't go inside at all. We find the circumscribed circle by where the perpendicular bisectors meet. And so that makes the center of your circle, which in this case is outside of the triangle. Okay, it could be the center of this circle could be inside the triangle if it was acute, or on the triangle if it was right. In this case, it's outside. And then it's also a larger circle in this one. Then we could do a similar idea, talk about the inscribed triangle here, or sorry, inscribed circle. So the inscribed circle is the inscribed circle's center is where the angle bisectors meet. It is always inside the circle. Inside the triangle. I can't get my language right here. Okay, so always inside. So the center is always inside the triangle. You can see that this littler circle is also fully inside the triangle. It touches each side once. And it is smaller. In the circumscribed circle. Those are just a few things you could take a look at there. You could say the inscribed circle is inside of the circumscribed circle as well. Number 5, triangle ABC is shown with its inscribed circle drawn. The measure of angle ECF is 72, which is labeled. What is the measure of angle EGF? So remember, when you've got tangent lines to circles, this central angle here and this outer angle are supplementary. So they're going to add to 180. So if I just put an X in here, so X plus 72, if you wanted to think about it that way, equals 180, which means that X is going to be 180 minus 72. So in this case, 108. Number 6, how do you know the values, or how do the values of X and Y compare? Explain your reasoning. So we know that this is an angle bisector. So we have an angle bisector here. We can tell because it's split it into 2 equal angles of 35. And when you have an angle bisector, remember that means every point on this green line is the same distance from both sides of the angle. And so I'll draw those sides on too. So here's the sides of the angle. So any point on this, let me change it to orange. So any point on this orange ray is going to be equidistant from the green sides. And we know that the distance to the ray is going to be a perpendicular line. So we know that Y is the distance, and we know that X is the distance. So these two are going to be the same because they are the same distance. D is the same distance from the 2 green rays. So we know X and Y are equal. Could have explained it that way. Could have also gone about maybe proving the triangles are congruent if you had forgotten that. So seeing these 2 angles and this reflexive side gave you that the 2 triangles were congruent by angle, side. So then you would know that X and Y are equal because they're corresponding parts. So a couple different ways you could think about explaining that. Number 7, points A, B, and C are the corners of a triangular park. The park district is going to add a set of swings inside the park. The goal is to have the swings be equidistant from the corners of the park. Find the location that meets this goal. So if we want to be equidistant from the edges of the park, we would want to construct the circumcenter. And that will be the point that's equidistant from all three of these. So to get the circumcenter, remember we need to construct perpendicular bisectors of each side. So let me go ahead and get my compass here. And then I like to just open my compass to wider than halfway on the biggest side. And then just draw a circle around all of the vertices, this same sized circle. So then you'll be able to find the perpendicular bisectors of each side. And let me change these colors so you can kind of see which ones are intersecting where. So let me change that. All right, so then we can do the perpendicular bisectors here. So where the blue and the yellow meet is a perpendicular bisector. Where the green and the blue meet is a perpendicular bisector. And then you don't have to connect the third one, because once we know where two of them intersect, we know that the third one is going to intersect there as well. So this point of intersection is going to be the point that's equidistant from each of these vertices. So this point will be the same distance from the edges of the park. So let me just draw in those lines. So this purple line, and this purple line are going to be the same length. All right, in number 8, it says in the diagram, the measure of the arc from A to B not through C. Okay, so from A to B not through C would be this arc. Let me make that a little bit less. Okay, so this arc right here is 80 degrees. What is the measure of angle ACB? So I want the measure of ACB, this angle here. So that is the inscribed angle. Remember, the inscribed angle is half of the intercepted arc. So we're going to do 80, half of 80, which is 40. All right, then number 9 says we have a solid that has curved sides. All the cross sections parallel to the base are squares measuring 3 units on each side. The height from the base to the top is 8 units. Find the volume. So remember, volume is area of the base times the height. So if your cross sections stay the same that whole way, it doesn't matter if it's curved. So we will do area of the base. So the area of this square is 3 times 3, which is 9. So area of the base, and then times the height of your solid, which is 8. So the volume is going to be 72 units cubed.